In Chapter 6, Section 2, we're looking at some properties of radicals, and one of the main things we want to learn to do here is to multiply, so find the product, and divide, find the quotient, and know the properties of radicals that allow us to multiply and divide. First of all, we need to know that if we have the nth root of some product, a times b, we can separate that out as the nth root of the first factor, a, times the nth root of the second factor, b. This equal sign means we can also go the other direction. That if we are multiplying two radicals and they have the same root index, and that's important, they must have the same root index, then we can put them under one radical sign with that same root index and multiply the radicands, a times b. Similarly, with quotients, if I have the nth root of a fraction, a divided by b, I can take the nth root of the numerator, the nth root of the denominator, and then divide. And again, it's an equal sign, so I can go in the other direction. If I am dividing two radicals and they have the same root index, I can combine them under one radical sign and take the nth root of the quotient of the numerator's radicand and over the denominator's radicand. Alright, so we're going to practice some of that with some of these examples. To look at the square root of 72, they want us to simplify. And that means find any factors of 72 that are perfect squares. So as I think of 72, I think of 36 as being the largest perfect square contained inside 72. Then we can take that square root of 36, and according to the product property of radicals, separate that out as the square root of 36 times the square root of 2. Square root of 36 simplifies to 6. Square root of 2 has no factors that are perfect squares other than 1, so that would be in simplest radical form. In our next example, we are asked to multiply. So we're doing this property in the other direction. If we are multiplying and the root indices are the same, then we can put them under the same radical sign and multiply the radicands. So 32 times 6 is 192. But we're not done because we need to see if there's any factors of 192 that are perfect cubes. As I look at my mental list of perfect cubes, I see that 64 is a factor of 192. Now I know 64 is a perfect square, but it's also 4 cubed, and that's important here. So 64 is the largest factor of 192 that is a perfect cube. I'm going to break this down into the cube root of 64 times the cube root of 3, and that gives me the cube root of 64 is 4. And there are no other factors of 3 other than 1 that are perfect cubes, so 4 cube root of 3 is my answer in simplest radical form. Alright, a fraction, well, the cube root of 81 over 125, what we just saw at the beginning of this lesson, is we can break that down as the cube root of the numerator over the cube root of the denominator. And 81, looking for factors that are perfect cubes, now be careful, 81 is a perfect square, but for cubes, 27 is the largest perfect cube that will divide evenly into 81. So break that down as the cube root of 27 times the cube root of 3, because 27 times 3 is 81. 125 is a perfect cube, and the cube root of 125 is very simply just 5. Simplify our numerator then. Cube root of 27 is 3, so our answer is 3 cube roots of 3 over 5. In this particular case, we have the square root of 72 over the square root of 6. We're going to go the other direction for that quotient property of radicals. And since they're both square roots, we could put them under one square root sign and call that 72 over 6. Now, when is it a good idea to do this and when is it not? Well, if these radicands divide evenly, then it's always a good idea. If those radicands would not divide evenly, it's probably not such a good idea. But in this case, 72 divided by 6 is 12, so it was a good idea. And we're looking for factors of 12 that have a perfect square in it. The largest perfect square contained in 12 is 4. So we'll break that down as the square root of 4 times the square root of 3. And the square root of 4 is 2. So my simplified answer is 2 square roots of 3. Alright, let's do the same kind of thing with some variables. So we've got the square root of 3ab to the 6c squared. I like to break this down into factors that are perfect squares and factors that are not. 3 is not a perfect square and has no factors other than 1 that are perfect squares. A is not a perfect square. B to the 6th is a perfect square because for variables its exponent divides evenly by the 2, that invisible root index there. And of course c squared is a perfect square. The square root of b to the 6th is b to the 3rd. And if you remember from our previous lesson, chapter 6, section 1, the square root of c squared is the absolute value of c, so we can guarantee that we get the principal square root. 3a does not have any factors that are perfect squares, so we just leave that under the radical sign, the square root sign. So b cubed, absolute value of c, square root of 3a, is my simplified answer. Alright, same thing, a little easier problem, so let's break it down. X to the 3rd is not a perfect square, but x squared is a factor of x to the 3rd. So I'm going to factor x to the 3rd as x squared times x to the 1st. 5 is not a perfect square, so let's put it in the non-perfect square radicals. And we can simplify the square root of x squared, and yes, that's the absolute value of x. And the square root of 5x cannot be simplified any further. Remember, if the root index is an even number, and this divides evenly, that's when we put the absolute value signs around the variable. Now, be careful with this next one, example 2c, because if you don't know how to factor correctly, you will be tempted to get this wrong. But the only thing I can factor here, since there's no formula for the sum of two perfect squares, there's no formula, it does not work. The only thing I can do is factor out the greatest common factor of 9. So let's make this the square root of 9 times the square root of x squared plus y squared. Square root of 9, of course, is 3. And no, the square root of x squared plus y squared cannot be factored any further. There is no formula for the sum of two perfect squares. And for those of you that think it's x plus y quantity squared, it is not. Remember, if you take x plus y quantity squared, take a binomial and square it, you get a trinomial. So that is as far as that will factor. Alright, so what does it mean formally then for a radical expression to be in simplest radical form, since that's what we've been working on? First of all, that the numbers under the radical sign, called a radicand, does not contain any perfect nth factors other than 1. So if we're having square roots, we don't have any perfect squares. If we're looking for cube roots, we don't have any factors that are perfect cubes, etc. We cannot leave the radicand as a fraction, and we cannot leave a radical in the denominator. And the process for putting things into simplest radical form is called rationalizing the denominator when we have a radical in the denominator. Remember, radicals sometimes represent irrational numbers. So to get rid of the irrational number in the denominator and make it rational, we are rationalizing the denominator. So if there are radicals in the denominator, find the smallest number you can multiply the denominator by to get a perfect nth factor. So perfect square, perfect cube, perfect fourth, etc. Then you need to multiply both the numerator and denominator by that number, otherwise you're not multiplying by 1 and getting an equivalent fraction. Then of course we have to simplify the radical, making sure that we're following step 1, 2, and 3 to make sure it's in simplest radical form. And that's the process that we need to go through to simplify our radicals and put them in simplest rational radical form. So let's take a look at a couple. Square root of 7/5. One of the rules said we cannot leave, in fact, rule number 2, we can't leave a fraction under the radical sign. So let's break that up with what we learned, the quotient property of radicals, beginning of this lesson. Make that the square root of 7 over the square root of 5. Doesn't get me much closer to my goal because rule 3 says I can't have a radical in the denominator. Now think of your list of perfect squares that I asked you to memorize in chapter 4, and again in chapter 5, and again in chapter 6, section 1. What's the smallest thing you can multiply the 5 by to get a perfect square? And that, of course, if we multiply by the square root of 5 over the square root of 5, in the denominator that will give me the square root of 25, And in the denominator, the square root of 25 is 5. In the numerator, the square root of 7 times the square root of 5. They're both square roots, so we can multiply them. 7 times 5 is 35. Now please don't get in the habit, because it happens frequently, doesn't mean it happens all the time. You do not always multiply the radical in the denominator by itself. So that's why in the rules I said ask yourself what's the smallest number you can multiply by to get a perfect nth factor. In this case, it is by itself, but it's not always that way. Alright, so let's look at the same process, only with some cube roots. The cube root of 6 over the cube root of 4. We don't have any factors of 6 that are perfect cubes. We don't have any factors of 4 that are perfect cubes, so rule number 1 is fine. 6 is not a fraction, 4 is not a fraction, so simplest radical form, rule number 2 is fine. But we have a radical in the denominator, so rule number 3 needs to be addressed. What is the smallest? What is the smallest cube root we could multiply 4 by to get a perfect cube? Now think of your list of perfect cubes. You've got 1. Can I multiply 4 by anything to get 1? Well, not without getting into fractions. We have 8 in our list of perfect cubes, and that sounds like a winner to me. We can multiply both the numerator and denominator by 2, because that would give me the smallest number I could multiply 4 by to get a perfect cube. 2 times 4 is 8, and 8 is a perfect cube. So in the numerator, they're both cube roots, so we can multiply the radicand. 6 times 2 is 12. In the denominator, they're both cube roots, so 4 times 2 is 8. And we multiplied by the same thing over itself, so we're multiplying by a radical-looking 1. When you multiply by 1, it doesn't change the value. Alright, continue to simplify. 8, the cube root of that is 2, because what number times itself 3 times is 8. 12 has a factor that's a perfect square, but doesn't have any factors that are perfect cubes. Perfect cubes are numbers like 1, 8, 27, 64. So none of those will divide evenly into 12. So to refresh your memory, this was the program we looked at, and this was the list we looked at earlier. It would be important that you remind yourself what these numbers are that are perfect squares, what are these numbers that are perfect cubes, perfect fourths, and perfect fifths. If you invest the time to get familiar with these numbers, it'll save you time on homework, save you time on the tests. So that's our look at multiplying, dividing radicals, and putting radicals in simplest radical form.